friend, welcome to this lecture, and in this lecture we will continue our study of wave equation. And if you recall, in previous lecture we have discussed the wave equation in infinite string, semi infinite string and finite string, and also we have given the variable separable method for finding the solution in finite string, and we have shown that by uniqueness theorem that the solution in the case of one dimension wave equation with finite domain, your solution, if it exists, has to be unique. So, it means that whether you apply D'Alembert's wave solution method or say a variable separable method, your solution come out to be same, and this will help us a lot in a sense that your variable separable method is generally easy to apply. So, when we have uniqueness in our hand, we try to solve our problem using variable separable method. Now, in this lecture we will discuss the problem wave equation in 2 dimension. So, here let us look at here, consider the vibration of a rectangular membrane, and the problem can be posed like this: utt equal to c square uxx plus uyy, 0 less than or equal to x less than or equal to a, 0 less than equal to y less than or equal to b here, and subject to the boundary condition that u0 y comma t equal to 0, u of a y comma t equal to 0, u of x comma 0 comma t equal to 0, u of x comma b comma t equal to 0, and initial condition are given as uxy equal to uxy 0 at fxy and utxy 0 equal to g of xy. So, here the thing is that here we are considering this kind of domain. So, here we have rectangular domain, and here we have x equal to a, it is x equal to 0, and it is y equal to 0 and y equal to b. So, your domain is a rectangular domain, and here we assume that here your solution is what, u of x 0, here solution in this is basically 0. So, it means that u of x 0 is coming out to be 0, here your boundary condition is coming out to be 0. So, that is what we have written here, that u of x comma 0 comma t equal to 0, u of x comma b comma t equal to 0 here. So, it means that here u of x 0 t is 0, here u of a comma 0 comma t equal to 0, here u comma 0 comma b comma t equal to 0, here u of 0 comma u of 0 comma y comma t equal to 0. So, here we have these boundary condition. Initial condition is already given that u of x y comma 0 equal to f of x comma y, and ut of x comma y comma 0 equal to g of x y. So, these are the initial condition given, and now we want to find out the solution of this wave equation. Now, here x is lying between 0 to a and y is lying between 0 to b here. Now, we look for a separable solution of the form. So, here we apply the variable separable method and write down our solution uxyt as xx y of y and t of t, and when you put this solution into your wave equation, your equation is now reduced to 1 upon c square t double dash upon t equal to x double dash upon x plus y double dash upon y. Now, let us assume that it is a sum minus lambda square, as we have already seen in the case of one dimension wave equation. We have shown that corresponding to the separation constant as minus of lambda square, your solution is coming out to be non-trivial. So, here we are using our experience, and we say that this separation constant is coming out to be minus lambda square, and then we try to solve this 2 dimension wave equation. So, here let me do it here. It is what you have utt 1 upon c square utt equal to uxx plus uyy. So, here when you write u of x y t, uxyt equal to x of x, y of y and t of t, when you put it here, it is t double dash xy divided by c square equal to, it is x double dash yt plus y double dash xt. Now, divided by xyt, you will get t double dash upon c square t equal to x double dash upon x plus y double dash upon y. Now this is a separable constant. Why we are separating this? Because this is a function of t only, and these are the function of x and y. So it means that these this will be equal when each quantity has to be a constant value. So it means that t double dash upon c square t is constant, x double dash plus x plus y double dash upon y equal to constant. Now here we can again consider several cases, that is case positive, negative and 0, and we can verify that the corresponding value for k which is a negative value will have a non-trivial solution. So I am leaving the part that you verify that for corresponding k equal to say positive and 0 we will have only a trivial solution. So now let us say that k equal to minus lambda square is a separation constant. So when we write it, then this 1 upon c square t double dash upon t equal to minus lambda square is written as t double dash plus c square lambda square t equal to 0, and using this I can write x double dash upon x plus lambda square equal to minus of y double dash upon y square equal to mu square, some other constant, because this is a function of x only and this is a function of y only, and these two be equal when these each one is separately equal to some constant value, and let us call this as separation value as mu square. So it means that now if we consider the last two equation, it is given as y double dash plus mu square y equal to 0 plus and x double dash plus lambda square minus mu square x equal to 0. Now to simplify these three equations, one equation is this t double dash plus c square lambda square t equal to 0, and y double dash plus mu square y equal to 0, and x double dash plus lambda square minus mu square x equal to 0. So to simplify, let us assume that let lambda square minus p square is equal lambda square minus mu square is equal to p square. You call mu square as q square, it is up to us. Then I can write lambda square as what? Lambda square as p square plus mu square, or we can say lambda square can be written p square plus q square. Now denote this value as r square. So we just write down a simplified expression for these three constants. So in terms of p, q and r, now your equation is written as x double dash plus p square x equal to 0, y double dash plus q square r equal to 0, t double dash plus r square c square t equal to 0 here. Now we already know how to find out the solution here. It is simple second order linear equation with constant coefficient, and we can find out the possible solution as u x y t as a cos px plus b sin px corresponding to this, and y double dash plus q square y we have c cos qy plus d sin qy, and corresponding to t double dash plus r square c square t we have e cos rct plus f sin rct here. Now here we have several coefficient here, basically a, b, c, d, e, f are all constant. So now we just try to find out the value of these constant. So here we try to use our initial condition. Now initial condition is what? u0 y t equal to 0. So when you put u0 y t equal to 0 means here u0 y t equal to 0 means x of 0, y of y, t of t is equal to 0. Now these cannot be 0, so x of 0 has to be 0. Similarly you have u of a y t equal to 0. So here again in a similar region you have x of a equal to 0. So x of 0 equal to 0 means your c is equal to 0. So here you simply put that since a cos px b sin px is equal to 0, so here we simply say no sorry here a cos px b sin px at x equal to 0 has to be value 0. So it means that a has to be 0, right. So that is let us write it here. We have what? We have a cos px plus b sin px and that is your x of x equal to 0. So x, so now let us say x of 0 is 0. So 0 equal to you will put a. So here a is coming out to be 0 here. Similarly you can write it that x of a equal to 0, then this implies that this p of a has to be lambda pi n pi kind of thing. So that we can get it here that u of a y t is 0, it means that p is pa equal to m pi. That is what we wanted to write, that pa is equal to m pi, where m is your integer value, m is coming from integer. So it means that p is now written as m pi by a. So which is what we have written, p equal to m pi by a, where m is from 1 to and so on. Now similarly, if you look at the other condition, that is this condition, that here we have assumed this condition also, that u of 0 y t equal to 0. So here if you look at here if you look at this condition, u of x 0 t equal to 0. So here we have u of x 0 t equal to 0 and u of x b t equal to 0 here. So here in a similar way, x of x y of 0 and t of t equal to 0, and x of x y of b t of t equal to 0. So this implies that y of 0 is equal to 0 and y of b equal to 0. Now what is your y of y here? It is we have written here c cos qi plus d sin qi, c cos qi plus d sin qi, right. Now put take this condition 0 equal to c. So it means that c is coming out to be 0. Now if we take yb equal to 0, it means 0 equal to d sin qb. Now if so, it means that for non-trivial solution you have to take qb as say n pi. So it means that q is equal to n pi by b, where n is say 1, 2 and so on. We are leaving value 0 because if you take n equal to 0, since it is sine function, you will get a trivial solution here. So it means that here we'll say we'll get q equal to n pi by b, n equal to 1, 2 and so on. So it means that here we got a equal to 0, c equal to 0, p equal to m pi by a, q equal to n pi by b here. So by using so it means that corresponding to each m and n we have a solution here, and let us call this solution as u m n x y t. So here using principle of superposition, as we have done for first case, we can write here solution as m equal to 1 to infinity, n equal to 1 to infinity, and let us rename this constant as let me write it here solution to make it more clear. So here we have written what? So here your x u of x y t is given as your b sine of m pi x by l, sorry m pi x by a, and if you look at the y component, you will get a constant here as d sine n pi y by b, and the component corresponding to tt, that is some c e cos of r pi ct by l. So here we have the corresponding say rct by l. So here we have e cos rct. So here e cos rct plus f sine of rct. Now what is the value of r? Here r is square is equal to p square plus q square. So we can write, since p square and q square we already know, so it is m square pi square by a square, and q square is equal to n square pi square upon b square. So it means the value of r is known to us, and we write m square pi square upon a square plus n square pi square upon b square. Now here this b and d will be merged with this e and f, and I can write this for each mn. Let me write it, it is u mn, and for each mn we have a solution. So let me write it, say solution as u mn x y t as follows. You simply write sine m pi x by a, sine n pi y by b, and in a bracket you write e as some a mn cos of r c t plus b mn sine of r c t, and since it is true for each mn, so using principle of superposition, if you sum over m equal to 1 to infinity and n equal to 1 to infinity, then the solution let us denote as u of x y t. So using principle of superposition, your solution is given as this, that u x y t equal to m equal to 1 to infinity, n equal to 1 to infinity, a mn cos of r c t plus b mn sin of r c t into sin m pi x by a and sin n pi y by b as we have pointed out. Now here the value of r square is p square plus q square, that is pi square m square upon a square plus n square upon b square, but still in equation number 39 we have two unknown, that is amn and bmn. Now to find out amn and bmn we will use the initial condition. The initial condition is that u of x y 0 equal to f of x y. Now if f of x y when you put t equal to 0, then when you put t equal to 0 this part is gone and we will have only amn. So it means that amn into sin m pi x by a sin n pi by y b equal to f of x y. Now using this I want to find out the value of amn. Now if you look at this can be easily obtained as we have obtained for first order. So here you multiply both side by say sin k pi x by a into sin l pi y by b and integrate between 0 to a and 0 to b, and using orthogonality we say that you can obtain our solution as amn equal to 2 by a into 2 by b 0 to a 0 to b f x y sin m pi x by a sin n pi y by b dx dy. So here this you can obtain using orthogonality of function sin m pi x by a and sin n pi y by b here. So here we are just using the orthogonality condition, that is 0 to a sin n pi x by a, sorry this is k pi x by a, and sin m pi x by a d of x is equal to 0 when k is not equal to m, and this a by 2 when k equal to m here. So using this orthogonality condition we for both in terms of x and in terms of y we have obtained our coefficient amn as 4 upon ab 0 to a 0 to b f x y sin m pi x by a sin n pi y by b dx dy. Now to find out bmn you use the condition that utx comma y comma 0 equal to gxy. So differentiate with respect to t will and using that utxy x comma y comma 0 is equal to gxy, we can write gxy equal to c times r m equal to 1 to infinity n equal to 1 to infinity bmn sin m pi x by a sin n pi y by b. Again you multiply by sin k pi x by a sin l pi y by b, and using orthogonality you can find out bmn as follows: bmn equal to 4 upon ab, and this cr is already there, so cr 0 to a 0 to b gxy sin m pi x by a sin n pi y by b dx dy, and hence the required series solution is given by 39, that is this equation, and the coefficient amn and bmn you can obtain by equation number 40 and equation number 41, and with this the solution of 2-dimensional wave equation we have obtained using variable and separable method. Now we will move to next problem, that is vibration of a circular membrane, and it means that here we want to find out the solution of the wave equation representing the vibration of a circular membrane. We use the polar coordinate system, say r theta, where r is lying between 0 to a and theta is lying between 0 to pi. So it means the problem is what? You have a circular domain like this, and here we have a membrane and this is vibrating. So this here this is a membrane and radius we are taking as r equal to a here, and we have this. Now to define this problem in an accurate manner we use the cylindrical coordinate to write down our wave equation. So in wave equation we have written 1 upon c square divided to u by divided t square, and here uxx plus uyy is now written in terms of polar coordinate, that is divided to u by divided r square plus 1 upon r divided u by divided r plus 1 upon r square divided to u by divided theta square. So that is the value of uxx plus uyy written in terms of polar coordinate system. Now initial and boundary conditions are what? Here boundary condition is that on the boundary, that is u a theta, t is coming out to be sorry 0 is coming out to be, let us assume that it is coming out to be f1 theta FAR. So, here we have assumed that UA theta is coming out to be 0. So, boundary your since boundary is kind of fixed. So, we can say that on the boundary your displacement is 0, and inside your r theta 0. So, here inside at some lesser value, say here it is given as f1 r theta. So, it is f1 r theta, and in velocity in terms of t, it is also given as f2 r theta. So, here your u r theta comma 0 is equal to f1 r theta, and w by w t r theta 0 is given as f2 r theta, and we try to find out the solution here. Now, again here we will try to use separation and variable method. Here the idea comes because the equation is separable, and the boundary conditions are also separable. So, using this information in hand, we apply variable and separable method to solve this problem. So, here let us apply for the solution of the equation 42, we use the following variable separable form, that is u r theta t can be written as r of r h theta and t of t. Now, when you substitute your r h t, then you will get r s t double dash divided by c square equal to r double dash h t plus 1 upon r dash h t plus 1 upon r square r h double dash t. Then you divide by r s t. So, you will get r double dash divided by r plus 1 upon r dash upon r plus 1 upon r square h double dash upon h equal to t double dash upon c square t equal to minus mu square. Now, since this left hand side is a function of r and theta, and the right hand is a function of t only. So, this can be true when it is separated by some constant. So, let us say that that constant is given by minus of mu square, and this again I am leaving it to you, that if you take positive constant or 0 constant, then we will have only a trivial solution. So, here our this equation is now reduced to t double dash plus mu square c square t equal to 0 and r square r double dash divided by r plus r dash upon r plus mu square r square equal to, now here also we separate r and theta, equal to minus h double dash upon h equal to k square. Now, here we use the separation variable, that is say k square. So, here now our equation is now reduced to, this last equation is now reduced to r square r double dash plus r dash plus mu square r square minus k square r equal to 0 and h double dash plus k square h equal to 0. If you look at here, your k and mu are arbitrary separation constant. Now, the general solution of these equations, equation t double dash plus mu square c square t equal to 0, r is small r square r double dash plus r dash plus mu square r square minus k square r equal to 0 and h double dash plus k square h equal to 0. If you look at, these are simple second order differential equation, and if you look at equation number 47, it is a Bessel's kind of Bessel's equation. Now, here we can find out the general solution of this equation as follows: T d equal to a cos mu c t plus b sin mu c t. R is given as p times jk mu r plus q yk mu r. Here jk and yk are Bessel function of first and second kind respectively of order k, and h of theta is given as e cos k theta plus f sin k theta. Now, using the solution listed in equation number 49, now I can write u r theta t is equal to a cos mu c t plus b sin mu c t into p j k mu r plus q y k mu r into e cos k theta plus f sin k theta. So far we have not utilized any initial condition or any boundary condition. So, now let us find out these constant a, b, p, q, e, f, and here we use that since u r theta t is a single valued periodic function of theta of period 2 pi, k has to be an integral value. So, it means that here E cos k theta and F sin k theta is a periodic with period 2 pi, provided your k has to be integer. That how you can check here, you can check like this, that since h theta must be equal to h of theta plus 2 pi. So, it means that E sin E of cos k theta, E of cos of k theta plus F of sin of k theta equal to E of cos of k, in place of theta let us write theta 2 pi plus F sin of k theta plus 2 pi. Now, you when you separate this out, you have E of cos of k theta minus cos of k theta plus 2 pi plus F sin of k theta minus sin of k theta plus 2 pi equal to 0. Then you can use the formula of cos A minus cos B and sin A minus sin B, and if you simplify, you simply say that you will get that k theta has to be n pi n theta. So, here sorry k has to be an integer value. So, this I am leaving it to you, that I am giving you the hint that using this and the formula of cos A minus cos B, sin A minus sin B, you show that k has to be integer value. If k is not integer, then this implies that E and F are some not 0 values. So, here you have to show that k has to be n. So, it means that here to have a periodicity in our problem, we have to assume that k has to be an integer value, say let us say k equal to n value, and also we assume that in a domain, in a bounded domain, your solution will be bounded all the time. In fact, it means that if you have a cylindrical domain and if we have a membrane which is vibrating, this vibration should not be unbounded. So, it means that inside the domain your solution will remain always finite, and if you look at the term yk mu r, and if you take r tending to 0, this yk mu r will be infinity, unbounded, going to be minus infinity. So, it means that this if yk term will be there, then we will have a unbounded solution. So, to avoid this unboundedness of the solution at center r equal to 0, let us take the coefficient of yk to be 0. So, it means that your solution will not contain any Bessel's function of second order. So, it means that your q has to be 0. So, what we have achieved here, natural boundary conditions, natural conditions are that your solution will be periodic, then this implies that k equal to n, and solution will remain bounded inside your domain. So, it means that your q has to be 0. So, it means that now if we look at the next boundary condition, that at r equal to a, your solution is going to be 0. So, it means that in a boundary your jn of mu of a has to be 0. So, it means that you have to choose mu in a way such that jn of mu of a has to be 0. So, it means that this must have since jn of x equal to 0 has infinitely many values. So, it means that let us denote that mu as the infinitely many zeros of jn. So, using all these information, your solution of the circular membrane is given as mu of r theta t equal to m equal to 1 to infinity, n equal to 1 to infinity, a cos mu nm t. Here mu nm is what? Is mu nm represent the zeros of jn. So, let us say that zeros of jn is mu 1m, mu 11, mu 12 and so on. So, we denote this zeros of jn as mu nm. So, let us write down our solution u r theta t equal to m equal to 1 to infinity, n equal to 1 to infinity, a cos mu nm ct plus b sin mu nm ct into e cos n theta plus f sin n theta plus into p jn mu nm r here. So, here we are using principle of superposition to write down this general solution. Now, let us multiply this p inside and we try to have less constant. So, now we write down our solution u r theta t equal to m comma n equal to 1 to infinity j n mu n m r into a n m cos n theta plus b n m sin n theta into cos of mu c t plus c n m cos of n theta plus d n m sin n theta into sin of mu c t. Now we want to find out a n m, b n m, c n m and d n m. Now to determine the constant we will use the prescribed initial condition, that is f1 r theta equal to f1 r theta is basically u r theta comma 0. So at t equal to 0 we have given two initial condition. So let us utilize this. So f1 r theta equal to m equal to 1 to infinity n equal to 1 to infinity a n m cos of n theta plus b n m sin n theta into j n mu n m r. So and next condition is f2 r theta equal to m equal to 1 to infinity n equal to 1 to infinity mu n m c n m cos n theta plus d n m sin n theta into j n mu n m r. So to find out AMN and BMN we use the orthogonality condition of Bessel's function and orthogonality condition of cosine and sine function. So here please note the following orthogonal property of Bessel's function. Here it is 0 to 1 x jp lambda mx into jp lambda nx, this is equal to 0 when m is not equal to n. Please note down here lambda m and lambda n are zeros of jp. So here orthogonal property is given in terms of zeros of Bessel's equation of pth order. So let us say that it is 0 to 1 x is the weight function, x jp lambda mx jp lambda nx, here lambda n m lambda n are zeros of jp. It is given as 0 when m is not equal to n, and it is given as 1 upon 2 jp plus 1 lambda n j square p plus 1 lambda n when m is equal to n here. So here this square is the whole square jp plus 1 lambda n whole square. So now using this orthogonal property, if I write any function f of x as summation n equal to 1 to infinity jp lambda n n x, then using orthogonality we can find out the coefficient here. So f of x equal to n equal to 1 to infinity a n jp lambda nx, and we can find out the coefficient a n as follows. So what we do, we multiply throughout by x jp lambda mx, and using the orthogonal property we can write yours 0 to 1 x f x jp lambda mx dx equal to am by 2 jp plus 1 lambda jp plus 1 lambda m whole square. Now we can simplify this problem and we can write am equal to 2 upon jp plus 1 lambda m whole square into 0 to 1 x f x jp lambda mx dx. So using this observation we can find out our coefficient amn, bnm, cnm and dnm, and here we can write down this is I am leaving it to you, that anm is written as 2 by pi of a square jn plus 1 mu nm whole square into 0 to 2 pi 0 to a f1 r theta jn mu nm r cos n theta into r dr d theta. And similarly bnm you can write 2 upon pi a square j n plus 1 mu nm whole square 0 to 2 pi 0 to a f1 r theta jn mu nm r sin n theta into r dr d theta. Similarly you can find out cnm and dnm. So it means that with these coefficient our solution is given by this u r theta t equal to m comma n equal to 1 to infinity jn mu nm r anm cos n theta plus bnm sin n theta cos of mu c t plus cnm cos n theta plus dnm sin n theta sin of mu c t, and this will represent the solution of wave equation in a circular membrane, in vibration in circular membrane. So with this I end our lecture here, and in this in next lecture we will discuss some more property of wave equation and heat equation. So with this I end this lecture. Thank you very much for listening us. Thank you very much. Thank you.